Hey everyone, and welcome to this explainer. Today, we're tackling a super specific but absolutely crucial objective for your Nutanix certification. We are looking exactly at NCP-MCI 7.5, Objective 3.3, which is all about IPAM, managed versus unmanaged networks. If you're an infrastructure admin gearing up for the exam, well, you're in exactly the right place. We're going to take a really deep, comprehensive dive into the architecture, the workflows, and honestly, most importantly, the specific edge cases that the exam expects you to know cold. So grab your notes, get locked in, and let's master this subjective.
Here's our roadmap for today. First, why IPAM matters. Second, defining managed and unmanaged networks. Third, real-world network examples. Fourth, exam traps and edge cases. And finally, number 5, key facts to memorize. Let's get right into it.
Part 1, why IPAM actually matters.
Right, so to kick things off, let's quickly nail down some of these core acronyms. IPAM stands for IP Address Management. We're operating here within AHV, right, the Acropolis Hypervisor, which is Nutanix's native virtualization platform. And in this environment, we've also got the CVM, the controller virtual machine, acting as that localized control plane on every single node. Now, traditionally, provisioning VMs, virtual machines, and handing out network addresses is just, well, it's a massive, intensely manual headache. Just think about the sheer pain of relying on tracking spreadsheets. You've got an infrastructure team trying to coordinate with a network team, passing IP assignments back and forth over email or chat. And all it takes is literally one outdated cell in a spreadsheet to cause an IP overlap that completely tanks an application. Plus, it just creates this huge bottleneck. Developers are sitting around waiting days just to get a subnet assignment for a basic test environment. By leveraging native IPAM within AHV, you're delivering a complete virtualization deployment with the network management fully included, right from a unified interface. You get to just throw that tracking spreadsheet right in the trash.
So how does Nutanix actually achieve this simplicity under the hood? While the Acropolis operating system, or AOS, works hand-in-hand with Open vSwitch, which we call OVS. OVS is essentially this software-defined switch running locally on every single node. You can think of it as the critical bridge connecting the CVM, the hypervisor layer, and all your guest VMs directly out to your physical network uplinks. By baking IP address management directly into AOS and OVS, the system seamlessly automates all that network provisioning. Think back to that scenario where a junior admin accidentally assigns an IP that's already taken because they were looking at, version 2 of the spreadsheet instead of version 3. In a traditional setup, boom, the application goes down the exact second that IP conflict hits the wire. But when you let AOS and OVS handle IPAM, the system is mathematically tracking every single assignment in real time, right in its own database. It systematically avoids those manual human errors that bring things down.
All right, moving into Section 2, defining managed and unmanaged networks.
In the Nutanix architecture, an AHV network is defined basically by a pure, strict binary choice based on its IP address management setting. If IPAM is enabled, you have a managed network. And that means it has a configured IPv4 subnet, and it utilizes an internal DHCP server. And just as a quick refresher, DHCP is the Dynamic Host Configuration Protocol, the standard system that automatically hands out those IP addresses. On the flip side, an unmanaged network is one where IPAM is completely disabled. In an unmanaged state, there's absolutely zero IPv4 configuration being handled by AHV, none. Instead, the network relies entirely on your traditional broadcast domains reaching out to your physical top-of-rack switches to go find some external or guest-level DHCP server. AHV essentially just takes its hands off the wheel and passes the traffic straight on through to the physical network. Okay, so understanding the strict mechanical rules that govern a managed network is super critical for the exam. To even create one, you are required to provide an IPv4 configuration, specifically the network IP and the gateway address. On top of that, you map exactly one managed network per virtual local area network, or VLAN. Now, when you set up your DHCP pools within this managed network, the rules dictate that you can have one or more non-overlapping pools. Now, you might be wondering, why would we even want multiple pools? Well, in the real world, maybe you want to reserve, say, addresses from .10 to .50 for static, hard-coded infrastructure, right? And then you want to spin up a dynamic pool from .100 to .200 for your more ephemeral temporary VMs. You can absolutely build both of those pools. But here is the catch. Every single address must be entirely contained within that network's larger managed subnet boundary. You absolutely cannot route IPAM assignments outside of that strictly defined range. So how does a managed network actually do its thing without totally disrupting your physical network infrastructure? Well, when IPAM is enabled, AOS uses VXLAN and OpenFlow rules directly inside Open vSwitch to actually intercept the DHCP requests coming from your guest VMs.
Because these rules grab the traffic locally right there on the host, all that DHCP traffic gets instantly rerouted to the internal DHCP server managed by the cluster. It essentially creates this really elegant containment zone. Now, I want to give you a crucial real-world troubleshooting tip based on this exact architecture. Because the DHCP traffic between the guest VMs and the CVM never actually makes it out to your physical top-of-rack switches, your external network teams, they're not going to see those DHCP broadcast packets on their physical monitoring tools. If they're running a packet capture on the physical switch to troubleshoot an IP issue for an AHV-managed VM, they are going to find absolutely nothing, zero, because OVS intercepted it locally on the host before it ever left the box.
Let's dive into Section 3, Real-World Network Examples. Let's walk through the exact chronological lifecycle of a managed IP address, kind of step by step. Step 1 kicks off at NIC creation, a NIC being your network interface controller, basically the virtual network card attached to the VM. Step 2, and underline this for the exam, the AOS leader assigns an IPv4 address from the DHCP pool the exact moment that managed VM NIC is created, assuming an address is available, of course. Why does that matter? Because it ensures the IP is firmly reserved in the cluster database before the VM even turns on. This completely eliminates those nasty race conditions where two booting VMs might try to grab the exact same IP address. Then, Step 3 happens when the VM actually powers on and requests an IP. OVS intercepts that DHCP request, like we just talked about, and hands over that specific pre-assigned address we just secured. And finally, Step 4, when you delete the VM NIC, or you just delete the VM entirely, that specific IP address is automatically scrubbed from the database and tossed right back into the pool for future use.
But what happens if you want all those robust tracking benefits of a managed network, but you really don't want a dynamic pool handing out addresses automatically? Well, the good news is the architecture totally supports this. You can configure a managed network, meaning you're still providing the IPv4 subnet and the gateway details, but you can intentionally choose not to create a DHCP pool. Think about a legacy database VM that absolutely, positively requires a static, hard-coded IP address, right? But you still want AHV to track it, so another admin doesn't accidentally steal that IP for a completely different server next week. This is exactly when you'd use a managed network without a pool. The infrastructure admin just has to specify the IPv4 address manually when they're creating the virtual adapter for the VM. So you get that strict manual control, but you keep the safety net of AHV's database tracking. It's the best of both worlds. All right, Section 4. This is the danger zone, exam traps and edge cases.
Picture this. You deploy a brand new cluster, and you set up an unmanaged network because, hey, the external network team just wasn't ready yet. Fast forward 6 months, they finally hand you the subnet details. Can you simply go in, edit that existing unmanaged network, and just check a box to magically turn it into a managed network? Take a second and really think about what your gut intuition tells you here.
The answer is a massive, definitive, absolute no. The AHV Administration Guide actually states this explicitly. It says, a network must be configured as managed or unmanaged when it is created. It is not possible to convert one to the other. So, if you get a scenario question on the exam asking how to convert a network, please do not fall for a distractor option that suggests using some secret command line conversion tool or a hidden toggle switch in the UI. There isn't one. The correct operational answer is that you have to use a migration workaround. You literally have to create an entirely new managed network with your desired IPAM settings, physically shut down your workload VMs, edit their VNIC settings to attach them to that newly created network, and then boot them all back up so they can pull their new managed IPs. It's a process, for sure.
Here are two more restrictive edge cases that just love to pop up as distractor options on the exam. First, when you're configuring your managed network IPAM settings, the prefix length cannot be greater than a /30. Why is that the hard limit? Well, a /30 subnet only provides two usable IP addresses, one for a gateway and one for a single host. That is literally the absolute bare minimum required to establish basic IP routing mechanics. If you try to force in a /31 or a /32, which completely breaks standard routing, AHV will just mathematically reject it. Second edge case, memorize this mapping rule. Each virtual network you create in AHV maps to a single VLAN and a single bridge. You cannot span one virtual network across multiple VLAN tags. It's a one-to-one mapping, period.
And finally, Section 5, key facts to memorize.
Okay, we have covered an immense amount of ground today. Let's really cement the final, most critical facts that you absolutely need to memorize before sitting down for that exam. Number 1, there is absolutely no conversion between managed and unmanaged networks after they're created. Remember, you got to build an entirely new network and manually migrate those VNIC attachments. Number 2, in a managed network, it is specifically the AOS leader that assigns the IP address at the exact time of NIC creation. This is what prevents those race conditions before a VM even attempts to boot. Number 3, Open vSwitch, or OVS, uses OpenFlow rules to intercept managed DHCP traffic locally right there on the host, which means your physical top-of-rack switches and your network team's monitoring tools are never going to see those broadcast packets. And number 4, an unmanaged network has zero IPv4 configuration natively in AHV. It relies entirely on an external or guest-provided DHCP server via pure network pass-through.
So, knowing all the strict operational boundaries and the really powerful automations we just discussed, which network configuration are you going to deploy for your next AHV cluster? Are you going to take that huge burden off your networking teams by leveraging IPAM, or are you going to pass the traffic straight through with an unmanaged setup? Think really carefully about how these architectural choices are going to impact your day-to-day operations and your overall application stability. Keep these concepts fresh in your mind. Best of luck on your NCP-MCI exam, and keep on learning. Catch you next time.